Hello everyone. Today we'll be solving a problem which involves calculation of the power spectral density of a pulse shape which has random coefficients. So we have been given with the pulse which is this and beta is random. So we'll first calculate the autocorrelation function in order to calculate the PSD for xt. So the autocorrelation function at a delay tau is given by this. So we'll plug in xt for beta n and beta m, and we'll have the expectation operator. So since g is deterministic, only beta is random, so we'll get the expectation operator inside only on beta. So this becomes at a delay of m minus n. So this can be written as this over two summations, and the expectation is gone because g is deterministic. So we have the autocorrelation function at delay of m minus n, the difference between these two time indices for beta n times beta m. So expectation of this by the definition of correlation cross correlation function is autocorrelation function is the delay between these two time indices, which is m minus n. We denote the delay by k, so the summation on m becomes the summation on the delay k, and this becomes r beta of k. Now these two can be copied here as is, and this is rx of the pulse xt at a delay tau. Now here this is periodic in t, because replacing t with t plus t makes no difference because of these limits from minus infinity to infinity. The extra t can be clubbed into these indices because these limits are from minus infinity to infinity. So we can define an average autocorrelation function because this is t periodic. So we can take the average of the autocorrelation function over period t by integrating from 0 to t and dividing by t, taking average of any function over a time period of t because this is t periodic. Next, we can plug the value of rx from the above equation, so we'll end up at this. Now here we have summation over n for this, so we can have this for n equals to 0. For n equals to 1 we'll have t minus t, so we can do a substitution of t minus t equals u, so this becomes du, and these limits become minus t to 0. Similarly, we can do this for all values of n, and this integral will have everything from minus t to 0, 0 to t, t to 2t, both ways. So these the argument is common and the limits are different, so these can be clubbed into a single integral. So these both can be represented by this because we can club all those integrals having the same argument by successive substitutions, because we can do the substitution for every n as I did for n equals 1. So next, this here I am currently denoting by Rg of tau minus kt, because this is similar to the autocorrelation definition, except for there is no expectation operator because g is deterministic. So as of now I am just denoting this integral by this, where this is the delay between these two, but this is not autocorrelation because this is not random. In this case this is a deterministic quantity, so this is just being denoted by this. So next what we need to do is, since we have the autocorrelation function, we need to calculate the PSD by taking the Fourier transform of rx tau. So we have rx tau, so the Fourier transform will be integral of rx tau times e power minus j2 by ft d tau, and we can plug rx tau from above. Now this does not depend on tau, so this can be taken outside, and we have this expression for us. So now we can replace the value of Rg from above as this integral. So now we have one integral from the Fourier transform and one from the definition of Rg. Now in this case, let's say I denote u as lambda, and let's say this is not there for the moment, then u plus tau becomes tau minus lambda or tau plus lambda. So this here becomes a convolution integral. So if we replace u with lambda, then this becomes d lambda, so it is easier to see this as a convolution integral. So what we are evaluating is the Fourier transform, because this integral along with this is the Fourier transform of this and this part is a convolution integral, and we are evaluating the Fourier transform of a convolution integral. So the value of the Fourier transform of the convolution integral by the property of Fourier transforms will be the product of the Fourier transform of these two functions. So this will have a Fourier transform of gf, this will have a Fourier transform of gf, but since this is delayed by kt, it will also have the delay factor, because this is tau plus lambda minus kt. This also has a delay of kt. So it's essentially, if it was minus infinity to infinity gu times g of u plus tau du, then this would have a Fourier transform of gf square. But then since the second one is delayed by kt, and we have to do the product of the Fourier transform of this, and because the Fourier transform of this is delayed by kt, because this g is delayed by kt, will also have this term for the Fourier transform of the second term in the product for the time domain, for the convolution in the time domain. So we'll have product in the frequency domain, and we'll have this delay corresponding to the second term in the time domain. So since we have an extra delay here, we'll also have the exponential factor in the evaluation of the whole Fourier transform. So we'll have this and this accounting for the kt delay here, because this has a Fourier transform of this, and we'll multiply these two Fourier transforms, because this is essentially the Fourier transform of a convolution integral in time domain. So this will amount to the product of the Fourier transforms of these two individual functions, which is mentioned for this we have this, and for this we have this, and we'll do the product of this to get this expression. So this is the final thing that we evaluated for Sx of f. Now we can use this expression in order to solve the problem. So this is the expression we evaluated. So assuming that it is an NRZ pulse, this will be sinc square ft. So we'll replace this by sinc square ft, which has nulls at 1 by t, but the problem says that the spectral density has nulls at 1 by 3t also. So this is not of much importance. This is not null at 1 by 3t. Now we'll focus on this term. So we'll have to calculate r beta of k. So beta n is given to us as this. In order to calculate the autocorrelation function, we'll use the definition of the autocorrelation function at delay k. So when we use this, we'll have alpha n minus k plus k alpha n minus k minus 3, and when we do the product, alpha n and alpha n minus k will this will be expectation of alpha n times alpha n minus k, which will give us a delta at k, because these coefficients are given to be uncorrelated. So they are given to be independent and identically distributed, but more importantly they are independent. So since they are independent, expectation of alpha and they are identically distributed, so these two are independent and identically distributed, so this will have an autocorrelation of a delta function. So the correlation will only peak when the delay is 0, which means that k is 0. So we'll have delta at k, and alpha n and alpha n will have sigma alpha square. So the expectation of alpha n and alpha n minus k will be sigma alpha square times the delay, which will be delta of k. Similarly, for this and this, the delay is k, and we'll have k square, so 1 plus k square with the same delay as k. this with this has delay of k plus 3, so k times delay of k plus 3. Sigma alpha square is common, and this along with this has delay of k minus 3, so k times delta of k minus 3. So now we know this RB, we can put this here, and it is for all k from minus infinity to infinity. So this is only finite for k equals to 0. This is only finite for k equals minus 3. This is only finite for k equals 3. We can plug all these values of k in order to get this. And this is given to be null at f equals 1 by 3t, so this becomes 1. And we have this equals to 0, which means k equals minus 1, which is the answer to the problem. So thank you for watching.